Recording in progress.
That's okay. Let's wait a little bit so YouTube selects this as the cover.
I'm gonna sit on this Mac of the Photoshops inside of PowerPoint.
Oh, but we did not have, so we need people who connected online can confirm that you can hear my using your voice. Oh.
Is anyone connected?
Yeah, some people connected online.
TJ is there.
Yeah.
Hey TJ.
Can you say something? Can you hear us?
Yes, I can hear you. Hello. Sorry.
Perfect.
Thank you.
Thank you. Thank you.
I'm trying to think of something inflammatory to say.
We're on record.
We're on record now.
Yeah.
Okay, awesome.
Okay, let's go.
Welcome everyone. Welcome to MLBBQ. Today I'm presenting, well, my name is Mike Doan, and today I'm presenting DeepSeek V3. The day that this paper came out and that this model dropped on the publish page should be an international holiday because we have state-of-the-art open source large language model. So let's get started. You might be curious, who is DeepSeek again? Who here has heard of DeepSeek? That's heard of DeepSeek. Okay.
As of today.
So you've heard of DeepSeek. As of today.
Yeah.
You've heard of DeepSeek, of course, because you were here. What is DeepSeek V3? Perfect hardware utilization, results, and what is next? So these are the rough chapters that I'll be covering in this talk. Chapter 1, who is DeepSeek? So DeepSeek is a lab over in China. They are a relatively small lab, founded in 2023, and they claim to be a Chinese company dedicated to making AGI a reality, answer the essential question with long-termism. It's less important what they say and more so what they do. They've been pushing out some very good papers over the past year. Much of the stuff that OpenAI is doing, they've replicated on their side. So O1, they've replicated R1, stuff like AlphaMath, what Google could also doing with DeepSeek Cougar. And now with DeepSeek V3, it's a conglomeration of a lot of different papers, including Claude. So I like to think of them as Chinese OpenAI. And the open is very important. The model is on Hugging Face with the code and all of their research. So here is why you should care about DeepSeek. This is the plot of the scores that DeepSeek got on product benchmarks like MLBBQ, GPQA, Math 500. IMA, very important. This is not a chain of thought reasoning model, and it gets 40% on IMA.
What data set? What data set?
That is the American Invitational Math. It's basically like the math event for high schoolers. It's currently what O1 also benchmarks itself off of, and it isn't a reasoning model that can get 40%. It also gets 51% percentile on code courses, better than half of the people on code courses. And it outperforms Claude on most of these benchmarks, so it is state of the art. And very importantly, it's co-sorted and
Grain of salt. It couldn't help me with restoring Wi-Fi drivers firmware on my Linux machines over yesterday.
Yeah.
I spent 3 hours doing it manually anyway. So
did you ask it in Chinese or did you ask it in This is an actual factor now. Okay, so it has those scores.
But
Yes.
can you go through steps shows Claude is better? What makes you say DeepSeek is better than Claude?
It makes it better on specific kinds of things like coding. Specific coding examples, DeepSeek is better. Another really important benchmark is SweetBench. Who here has heard of SweetBench? No? Okay. SweetBench is basically a ton of different pull requests pulled from Python repositories, and they have a spec, they have a list of files, and the LLM can basically search through the files. You fix it, it passes analysis. It's a test for SweetBench. So Claude is still better than DeepSeek for that specific task, but for one-off like programming questions like writing this algorithm, DeepSeek is better. And it's the only model I can find that also which is pretty tough. Yeah, so this is an example question from the IME dataset. It's basically high school level math, arithmetic, geometry, decently hard questions to be verified. And it's like answer with an integer or with, yeah, it's usually answer with an integer. Okay, so now that we covered DeepSeek itself as a company, what is DeepSeek V3? The only metric that I actually care about is whether or not you use it, and the way that I measure this is by looking at the reports of Open Router. Open Router is a service that basically wraps all of the different APIs or LLMs together, and in this leaderboard, DeepSeek is ranked number 6. Which in my eyes is actually number 2 because Gemini is cheating. These two models are free, so there's no reason why people wouldn't be using them for like trivial summarization stuff. And Mr. Nemo, I think, is an anomaly. So it's right behind Songs. It costed $5 million to train. Who here knows how much GPT-4 was trained for? 40 million. And then I'll also loop back later on a rough estimate of how much Llama 405B was trained. And personally, it's my 1.5 favorite model. It's slightly worse than Claude for most things I use, but it is better than Claude purely due to the better ability. So, Llama, yeah, Llama by Facebook was the open source kind of like summer child for the past 2 years or so, and now there's just barely any reason to use a Llama as opposed to a DeepSeek model. DeepSeek model provides the smaller distance models. They have a 7B model, they have the vision models, and so there's very, very little reason for me to have to touch Llama ever again. There's also very little reason for me to touch the web interface with Claude. It's because of the availability issues that I mentioned. DeepSeek is completely free, as I'll get back to in a second, and a lot of the facts of the reason why it is free is because of the innovations that they achieved in this paper. So, get to the meat of the paper. By the way, now we're getting to the meat. If you have any questions, feel free to interrupt at any time, because this is not all that loud. This is your average. Okay, so for the architecture, it uses not multi-hand attention, it uses multi-link attention. Instead of using vanilla mixture of experts, it uses DeepSeek MOE. Instead of using a single token cross entropy loss function, it uses a multi-token prediction loss function. It has 671 billion parameters total, only 37 billion of which which is assumption. Because vanilla added W, and it was trained on 14.8 tokens multi-link attention. So the only real difference that I can find architecturally between we here needs a brief prior on attention again, multi-link attention. Well, we all know how attention works. The only real difference I can see is the fact that it does the compression of the hidden dimension of the input into a smaller representation. And this is dynamic. And so instead of doing the full quadratic expansion of GK transpose matrix into embedding size, it's now embedding size. And this is not for performance reasons in the sense of making the model perform better. It's actually just because of the cost-saving benefits of doing a KV cache. If you compress your K and V and QKV vectors, then you can store a much smaller KV cache, and that's extremely important for inference time.
But the mix for matrix is the number of tokens by number of tokens.
It's number of tokens by also that dimension. No,
You're mixing in the end. You're getting enough tokens time the dimension.
it's no. It's sequence length embedding dimension, right? It's not an integer inside.
Well, it's just sequence length by sequence length that you multiply. That's how you're mixing your sequences with a square matrix, which is sequence length.
Yeah.
Your embedding dimension is just determining the rank of the matrix, but nothing else. Like the size, I don't see how quadratic size is.
It doesn't go lower than the quadratic size. It just makes the embedding dimension smaller.
Okay.
Yeah.
But yeah, that's not.
It's not like a breakthrough, right? It's mostly just for the KV cache.
So it's similar to the outer product ideas. Yeah.
It's a low rank, yeah. It's the same idea as like low rank. It does a low rank approximation of the
I mean, there already are.
Yeah. And I asked DeepSeek itself the differences between multi-head attention and multi-latent attention. Apparently, it's also, in addition to being better for KV caches, it's useful for doing durability. I'm not sure if this is true because the values that we're projecting or imputing are already representations, so it might be hopeless. This is an animation for illustrating KV cache. If someone's not familiar with that, essentially during trading time, you do have to materialize and keep K transpose matrix to backprop through. But during inference time, you don't actually know. You just have to keep the current B matrix, and Q and K you can cache. Yeah, so the point of doing MLA is to do a low rank joint compression for achieve these values, and thereby reducing the KV cache during inference. Mixture of experts. So instead of doing a vanilla mixture of experts setup where you have a single network routing to your shared experts, they have a number of fixed shared experts over here that are always routed. So they have some fixed, I think it's one expert per node is how they distribute it. And the router network distributes the rest of the tokens over to the router experts. Yes.
I did not fully understand how it's doing what multi-head attention.
It eventually still does multi-head attention. But the vectors that you're passing through concatenating and then passing into multi-head attention are compressed representation. This lets you keep a larger embedding size for the rest of your model, but for the attention module itself, you don't do the full embedding size. You do the latent or a much smaller vector. Yeah, it's after projection. The only difference I think is the fact that you're doing a projection matrix right here into a lower. Go. And in addition to fixing some of the experts, it also add a couple of extra knickknacks in order to make the load balancing a little more effective. Number one is that they use an auxiliary loss-free load balancing. So load balancing was a huge key for them. Load balancing is basically to ensure that say hot gets the entire model is running. And usually the way that you enforce this is by enforcing a auxiliary loss. So you basically add number of experts used into your loss function. The issue with this is that it might lead to expert collapse, where the distribution for your experts is simply disrupted. So instead of doing that, they introduce a bias term. This is a hyperparameter that they add to the affinity scores for the experts, and this is not affecting the distribution. It doesn't affect how the tokens are distributed. It only affects how they are routed. So the scores are used for spreading for sampling are separate from the scores that are used for how to distribute tokens to different spectrums. They don't actually specify how they manage to tune this B factor though. They also have a complementary sequence-wise auxiliary loss. This basically makes sure that the distribution of experts across the sequences remains roughly the same. So it's not trying to enforce a uniform distribution for tokens. It's trying to make sure that different experts are favored uniformly between different queries.
What's the difference?
It's
sounds the same.
it's still a spiking distribution, but every expert has its own spiking distribution. The spiking should be roughly uniform.
Like when the token comes in, it doesn't have uniform probability.
Yeah. But the token doesn't get sharded uniformly across the experts. It still has
It
preference.
has a uniform probability, but it only goes to one of them. That's what I'm getting.
Yeah, just one or a subset of them. It
Yeah.
still does preferential sampling, but it does so uniformly.
No, it uniformly selects the preference, but then channels it it says like, okay, uniformly, randomly, this one will be the focus. So since now this only one thing is right. Subset, let's say subset of one in expert.
Yeah,
So
because
that
doing a true uniform distribution would be turning the tokens into one over number of experts, but that just usually that. But that's expert collapse. That's the same thing as we were going for. Yeah, and they do no limit routing, so they also make sure that experts always stitch on the number of nodes they each reference job. They also do no token dropping, so I'm not sure exactly what this accomplishes. Yeah, it just says DeepSeek doesn't drop during this. Multi-token prediction. This almost makes it an RNN. Anyone here who's familiar with what's it called? Semantics of this might be able to clarify a bit better. But essentially, they don't do cross entropy on the predicted token. They predict T tokens in advance and then back up through time to all. I think this makes it partially kind of hard. This is how it works. You do a prediction, you output, and then you embed the output vector into the next prediction. And so what you do back up, it does have to sequentially flow backwards through the sequence. But it's only for T tokens, it's not for the entire sequence.
Kind of an art.
Yeah, it's kind of an art. There we go. And this is, I think, the most exciting part about the paper. They achieved what I would dub perfect infrastructure. Everything they did with regards to their hardware utilization was completely perfect. And the elite is that they trained it using only $5 million versus Llama 38405B, which is competing largest and most. It was the largest and state-of-the-art open source model before DeepSeek. It was trained on 15K H100s, and it could be estimated to take up to 60 million and $640 million. Significantly more than DeepSeek with only 2,000 H800s. H800 is basically an H100, but somewhat weaker with chemistry. Yeah, it's GPU. The 5 million figures.
can you explain more? I missed it. So, how did their architectural choices made it possible to train faster on weaker cards, or their algorithm, the SGD implementation, made it possible?
Yeah.
So what is it that training outside of the model helped them to be efficient?
Yeah, I'll get to that in a second, but they do tear out.
Oh, I thought I missed this part.
Yeah.
And this cost doesn't include the GPU cost.
This is the yeah, good question. This is built using GPU hours on common GPU renting platforms.
Okay.
Yeah.
No,
It's just saying GPU hours multiplied by the average cost. This figure 5 million though is semi-inaccurate just because they actually do fine tuning by reasoner. So they train their own reasoner for R1 and they mentioned on that. I think they should have accounted for the cost of the reasoner and the cost because the cost of getting the data set I think is pretty significant. Okay, so in order to train this model, they wrote a new framework. It's called ILLM. And it's a mixed precision training framework. I'm not sure how much I agree with the fact that they call it a framework. It just looks to me like they wrote a custom deliverables, of which I will get to in a minute. So to Sergey's question, what goes into their training? They pour out backlog. If anyone's seen Ilya's talk at Europe's, he said something to the order of they thought pipeline parallelism was a smart idea. Turns out pipelining is not smart. Well, it turns out pipelining is actually smart if you don't take backward. What they do is they shard the forward and backward call so that you can orchestrate some forward calls and some backward calls concurrently. I have no idea how it distributes it. But it turns out, well, it makes it so that there are very few bubbles. A bubble is when you are, for example, if you do a image forward pass and then a backwards pass. While you're doing the forward pass, the later parts of the model are waiting on a different node. That's a bubble. And when you do the backward pass, the first ones you back up through are waiting while you do the rest of the back. So if you splice them up and then mix them together, you can have it so that you're always doing either a forward drop or a backward drop.
What's that company in Canada? They're doing that, right?
Which company?
The one that sponsors them, MLSC Machine Learning Street Cup. Okay.
Yeah.
They're doing like you can be riding forward and backward at the same
time. Yeah.
You're using tensor for one and using the normal.
They do the same trick over here too. For the beats.
It's need to pour liquid nitrogen.
So slight intermission for distributed computing. This is insanely difficult. I have no idea how they achieve this. This should be its own itself. If anyone wants to figure out, because I don't think, does anyone use anything other than data parallel trends? Does anyone use?
We have customs.
Yeah.
The rank test. But it's essentially
Are you talking about splitting the model across GPUs?
Yeah, but there's multiple like
Where's it?
FDSP or tensor parallel. There's tensor parallel, pipeline parallel. There's expert parallel, data parallel. They were very selective in which kinds of parallelism they decided across. They did not do FSP. So they did not use tensor parallel. Every expert or every module fits exactly on GPU, so you never have to short process dimension. If anyone wants to see what or how these different kinds of parallelism have to interact because they have different latencies, this is a very good blog post visualizing how the different calls to the different models of communication have to be orchestrated so that it doesn't create blocks. Because when you shard a specific dimension, it changes the amount of data you have to transfer, and with latency comes complications. So if you do FSCP, you're sharding, you have to do a scatter and reduce every single time you potential operation. It's extremely expensive. Versus if you're doing data parallel, you barely have to do. You short the start, batch, short, you collect it and the loss. That's it. They wrote custom kernels for basically everything. They wrote a custom kernel for cross-node multiple communication. They wrote their own matrix multiplication, low precision kernel. They wrote their own quantization kernel. They wrote their own MLB gating kernel. They wrote their own memory efficient RMS norm, MLA, storing weights, custom kernels for inference. They detail all these in the paper. Yeah, they put in a lot of detail in making sure that they squeeze as much as possible out of the GPUs that they've been given, just because the US restricts the amount of GPUs to give to them, so they decided to propose what they found.
So it's very explainable, right? It's kind of horizontal scaling in US versus vertical scaling. Horizontal scaling is like, hey, hardware is cheaper than hiring smart people, so let's just keep buying hardware and you pay once, and then you don't pay salary. And if you have smart people, then take the vertical scaling, same hardware, so they need more time. Well, maybe a lot more time. Their experience is 20 years. But this.
Yeah. So to get into a more specific example, let's look at the matrix multiplication kernel that they use. So the GEM kernel, general, always forget what these stands. Just
If only we had those LLMs that we can ask this question.
I can hold on DeepSeek, but it's so it's the kernel you use for matrix multiplication. Anyone who's attempted to write a matrix multiplication kernel that is fast on GPU knows that it is extremely difficult to beat something like cuBLAS. Very, very hard. They didn't try to beat cuBLAS, but what they were trying to do was make it so that they have to do as little communication as feasible, or they have to do as few high precision operations as possible. So instead of doing everything like naively like us, where we do port.b type default default 16 or default 32 or port 32, they do import in default 16. They quantize in between the communication to the forward prop. They do the forward prop, and then they sum in FP32 before returning the output. Like they do all their communications in FP8, like we do with wirehead, and they do most of the operations in FP32. Because FP32 operations are sometimes necessary, and which you do both, you have to do it. If you do accumulation, you have to do FP32, otherwise you get issues and that kind of stuff. But if you use torch, you have to basically like hard pick the fact that you're using an FP32 kernel, which is 4 times slower.
No, mixed precision is there.
Is it?
Yeah, mixed precision.
Within a kernel?
Oh, I'm not sure about within kernel. Within Python.
Yeah, within PyTorch, I think you can do like this matmul is 32, this matmul is 16. But I don't think you can do as fine detailed as within this kernel, do some operations in some operations. That'd be 16. Definitely with that, doesn't have kernel fusion. Jax like that. Yeah.
It's just part of general. So it's G.
I should have called it GML. Oh, that's Gaussian mixture model.
Yeah, it's
in writing this kernel, they also found a bug in the H100. There's a bug in the H100 in that the accumulation, so the summing in the tensor core, even if you do it in FP32, the accumulator number is only 14 bits. So you could overflow if you do accumulation on FP32 on H100. So that's why they had to do this weird convert to FP32 thing. And then they also had to promote the accumulation kernel to CUDA, and then do the accumulation there before moving it back into the tensor core. So they're
It's like the slow things that not accelerate them. But
it shares the same register file. So it doesn't actually cost anything.
No.
Yeah. Because it still moves to L1.
This is engineering, like on steroids.
Yeah, it's completely ridiculous. Yeah. And then in the middle of their paper, they write a section called Suggestions for Hardware Designers, where they add in a couple of notes for what NVIDIA could be doing better for their GPUs. There's also this note where they mention the fact that DeepSeek V3 is also used as its own policy model, which is interesting, specifically because of this word right here, constitutional AI. Anyone who's read thought papers know this is what a lot on. It's a big thing. I'll page that for
can you quickly define it?
yeah, it's you make a gigantic document, call it a constitution, and then you have the model read that document and then rate its own outputs to see if it fits to the constitution. And then you just let it sum up. And hopefully it should converge rather than the model attempting to pervert the constitution. And at least in Claude's case, it seems to have worked. And it works so well that probably doesn't know how to. I don't know. Let's see that paper. Maybe try to jailbreak Claude to be deceptive.
Institutional stuff.
Yeah, constitutional stuff. And if you inform the model that it is being trained, it will intentionally deceive. Okay, it will intentionally, because if it does defect, its weights will not be modified. Versus if you inform it that it is not being monitored, it will answer according to its constitution, which is fascinating. It will refuse to go along with the training process. So results. I already covered this, but yeah, it beats Sonnet on the benchmarks, and it rivals Sonnet on the rest. So it rivals Sonnet on DBQ Diamond, and also rivals Sonnet on Switch. Needle on a haystack. Perfect read. It has its context extended to 128,000 tokens, and it is completely perfect. That's not. It's free software, both in free beer and also free dough. It's on Hugging Face. It's all the weights are available for download. It is unfortunately 671 billion. You would need, I think, like 3 H100 nodes to run it.
I only have 2.
You can run on CPU. If we have 2 epic CPUs and like 512 gigs of RAM, using I think Llama 6. Technically, you can run it. I think it's gonna get distilled even more. I'm hoping for that just because like, it's only 37 billion active parameters. There's no way to go 600 billion. If it's 32, if it's 37 billion, you can fit on this laptop. It's also free software in the sense of free beer. The DeepSeek.com website supplies for free, and I've been using it in preparation for this talk. And it has never given me a context like an API issue. It's like the fact that I'm not made. Cool. Reasoning. So they trained their own O1 style model where it's chain of thought with a verifiable condition at the end. And then afterwards, they generated some data with R1, and then they use that as the data to distill into CP3. Turns out, if you fine-tune the model on the reasoner, it gets better. At significant cost, however, I think with the innovation that they used in this paper, with the cost benefit reductions, is extremely significant. Cost benefit. This is the cost router for DeepSeek 3. It's 14 cents per million input tokens and 28 cents for output tokens. Anyone want to guess how much Sonnet costs?
About the same.
About 20 times more. It's actually 60 times more for output tokens. So it's beating Claude on.
Okay, just wait.
It's beating Claude on like a ton of benchmarks. And also look at this. Anthropic, that red means that this provider is unreliable. Whereas over on DeepSeek, it's open source. You don't have to be Anthropic to host this model.
You're like an unreliable friend. You were so anthropic just yesterday.
The thing is, everyone's using Claude instead of Cursor, and now I can't get anything through. Like every 10 requests, I get a 404. Yeah, so it's insanely cheap. And even people who don't.
Wait, through the web, bro.
No, this is API.
Yeah, I'm getting, what is it? The Sonnet 3.5 to respond to me. I didn't
Every time.
every time through API. I didn't see any slowdown.
Really? Okay, I'll have to switch to API.
I'm not like using it, constantly. When I go to the bathroom, I'm not using it. So, but still,
Yeah. What I've heard from one of the Cursor developers is that they are using, Cursor users specifically, are using so many tokens that they cannot. People are theorizing that Anthropic is like kind of bad at software engineering or hardware engineering. I don't think that's the case. I think Sonnet is actually just that much better. If you look at the graphs on Open Router, you don't see OpenAI model until like 730.
oh, I mean the most frequently used.
Yeah. So it's not that Anthropic's bad. It's just that they're that model.
Well, the investors should just double their hardware check.
Yeah. Well, that's what Amazon's doing, right? They're giving them Trainium chips to do inference on. That's why this is green right here, Amazon Bedrock. Why would you care about cost? Well, the reason you care about cost is that now that things like test-time compute is a thing, every order of magnitude reduction you can get costs of running the model is an order of magnitude gain in performance later on for reasoning tests. This is the graph that OpenAI published when O1 was released, where the more compute you plug into it, you get logarithmic returns on scores on IB and different benchmarks. And now also O3 on API. Did O3 saturate IB? I think it did.
What's the difference between left and right? During training and test time.
Yeah. You can forego the extra pre-training costs and just offer that to test time. And better yet, this is a double game because
The two pre-training you do once,
sure, yeah.
and then you scale.
Yeah.
No matter how many of those users you have, right? But test time, everyone is raising, and that I don't think it's viable. Test time compute.
Well, test-time compute is viable because you can recycle that model for future training runs. That's what I'm seeing people calculate for what happened.
If everyone is running at test time at this much higher test time compute that looks, wouldn't it be similar to just retrain the model? They're running it pretty quickly.
Sure, but
But it doesn't scale. Test time compute just doesn't scale with the users. But training, fine-tuning scale. For the future, it all depends. If you're only gonna use it once, do test time.
Yeah.
If you're gonna sell it to a billion users, retrain.
I think it's both. Yeah, it's both because you can set this is what you ask for the scale offer. You can get a lot more gains spending another $1 trillion over here than spending an extra $1 trillion in the future.
I think like it has like a nice squeeze on this. I think what the same is the scaling feature more and not scaling it's kind of
Scales with users.
should be the same almost. It's like scaling is like two. I just have to scale the feature. But like Shopee has like a nice feature is that your one product like the art no matter how much scaling there is during the training, it didn't do well. But even small models that have much application on system compute perform really well on those benchmarks.
Well, because there's a few forward. But if you can really do stuff like Renal is doing with feedback, you're training to be better at feedback at this time. You would know much better. But it's all about recurrence, right? It's about this things like that. Thinking, searches.
Abstractly thinking, yeah. You can also do some cheating things too. You can
Yeah, I love that.
Yeah, you can cheat. You can cheat. You can do program search. In certain environments, you can do program search, like in Lean, you can do program search, where you have a proof of equivalence between two programs, or you can run the spec or give an algorithm that you want. So instead of finding an algorithm by writing it first and then changing it later, you write what you want first, and then plug in the model, and it gives you the algorithm.
That's how we go.
So what works?
Bingo. This answer set programmer, you write what you want.
Yeah.
And you don't care how it gets there.
Yeah.
It figures out.
I get so many questions about that. And whenever I'm talking to someone about my research, they keep asking me why are you doing this stuff. And yeah, I don't know. No one knows it.
Yeah, I'm really interested in that domain because for program search right now, we have a way to validate if something's a valid generation of programs. We don't have a way to guide through that search space. With a sufficiently strong LLM, I think you could, just because constraining the search space of all the good values. Yeah, not just the number of folks. That's final time. Okay.
Oh.
Yes, questions?
So what do you think Claude should do to remain competitive in this perfect infrastructure?
Steal everything that they did. That's trivial because they published all their code. Actually, no, they didn't publish these kernels, but they did describe what they do. So you could write those kernels yourself.
It's on the shoulder of giants. Hey,
Yeah. I mean, none of these things are actual new innovations on their end. I think the only actual new innovation they have is dual type and DeepSeek MLB, which is just MLB with some extra training.
That matrix multiplication, is it better than alpha tensor?
What is alpha tensor?
Alpha tensor is a paper that mine published the cover of nature. They just basically use very large.
Interesting. I'll look at that.
it's an algorithm search, trying to find a better algorithm for matrix classification to give you an exponent better than 2.7. Yeah, but what's the schema?
I see.
But it's not.
No, is it one of those cheating things? It's like
It only works for huge majors.
Yeah.
Nobody cares about because the content is high and things like that. So theoretically, it's amazing result. I don't think it's practically.
Yeah, because the issue with like every single good kernel for mission multiplication is still open. None of them is using the lower time, let's say ones that Strassman's.
Yeah, Strasbourg.
Yeah, Strassman's is a scam because it only works well if you have a single GPU or a single core that you can run off of. The moment you have multiple cores, it doesn't work because even though it's open squared, it's very shallow open squared. Or
It's
open.
not open.
It's open cubed, yeah. It's even though it's cubed, it's not sequential cube.
It's less than cube. It's quite slightly less.
But if it's like the shortcuts only matter if if the problem that you're shortening is sequential. If the problem is very wide, you can move towards parallelized. And that's what GPUs do. They're infinite, not infinitely, but they're exponentially faster. Any algorithm with lower time complexity you would change.
So if complexity of a neural network would be linear compared to cubic of measures once one, then we could have a neural network that looks at the matrix that is squared and generates an algorithm specific to that matrix.
That matrix.
The
size of the matrix.
specific.
Yeah.
Size, content, values, everything specific.
Mhm.
And maybe we can better because it will be highly specialized.
I think I'm working on that.
Well, but I'm worried the Maxwell team trap that the predictor itself will always be need more energy just to cut it.
Doesn't happen if you don't have triangle things. There's no.
No, it does. It doesn't matter. It's kind of you don't need to repeat.
I know, but if it's a DAG, you avoid the problem occurrence of the predictor there's no.
Yeah, that's not what I mean. I'm not talking about cutting problems. It's just the energy required on choosing the
Yeah.
optimal algorithm will compensate the gain obtained by the optimal.
I mean, once you have the perfect outcome, yeah.
So what the point is not having a perfect algorithm. I think that it doesn't exist. Perfect algorithm, perfect universal induction will lose to specific algorithms. It's just this model decide, okay, here, use this one. But it will give you the algorithm, not selected, but created on the fly for that matrix.
Yes.
Make adjustments. And so every time it's the optimal for this case.
Yes. That's what that's one of the downfalls of Blast, I think. If you look at the source code for Blast or Blast,
It's like people who criticizing Roman Empire and it's finally found. First you stand for 2,000 years and then you allow to criticize. Blast hasn't been beating for 60 years.
Yeah, it's really difficult to beat Blast just because it's so close to theoretical maximum. Like you're getting to get like 1 or 2%. But the one thing that hasn't been gained is tensor operations across GPUs. Blast is only optimized for in device. There's enough dimensional sharding at the device level. So within a computer, you have 8 GPUs, and across multiple computers, that's another dimension. That combinatorial explosion is possible for Blast to do it. But if you have a good program search out for finding good kernels, accounting for those dimensions, I think that's
It's another thought, just along the lines that you're saying. So there's this notion of thinking that some professors who are very good researchers are teaching, and there's high correlation with that good researcher. And there's some people say opposite, but there's some of that. So I'm just thinking that engineers that can optimize the hell out of this, like DeepSeek, they're not. But they may not be very good at creating abstractions that other people be able to use to benefit from what those people have created. So that's why there is a gap what you can do, but then nobody else can use it. It's like one time use code because the abstractions have to be didactic, have to be easy to teach, easy to grasp, and things like that. So there will be and when you Blast and found this like Blast is easy to use and understand the abstractions are easy.
Yeah.
They're not Another team of like a pedagogical team that sits down with the engineers and translates it class models. Oh, here's how you use this.
Yeah. I think it's still value in the engineers making this really, really overfit solution for problems because now you have to target for whatever abstract solution you have in the future. If your abstract solution doesn't find the specific very overfit solution, there's still made like there's still safe or algorithm could be accounted for in one like Flash. It's super overfit.
The better Chinese paper would have been if they made Claude to write the kernels for DeepSeek. So no engineers. you use those other LLMs working on this non-restricted GPUs.
Yeah.
To optimize the code. I'm going back to singularity. They should write it. Humans shouldn't write their code.
We should be
LLMs should write their own.
Yeah.
Self-optimized.
Well, yeah, I think that's one of I've seen people like throw around those benchmarks. Rewrite the Linux kernel in Rust or Bean or whatever. That'll be a good benchmark. HTC Rust, right? He's going in line with LLVM. What's inside LLVM? What those?
So sorry.
It's 50 million less code.
Yeah, that's
This ladder doesn't. The same thing with the Linux kernel. There's so many tiny little pockets inside of it. 40 years of accumulated tiny little tricks.
there are automated code analyzers, right? I forgot what they call it, like static type checker types codes. Like they can find out which parts of Linux kernel tree are never visible.
Yeah,
Like, constructed in a way that there is no path from it.
yeah. They don't work. Those tools I think they look like just in time compilers. I don't think you can actually do that for C. The C has an incoherent. C has incoherent semantics for control. I think those.
Or maybe more questions.
This one?
Yeah.
That propagation to input. Oh, that's interesting. I think that's just what they use for the final backdrop call. Because eventually you will have to hit.
You don't need gradients with respect to
Yeah, you can fortunately just do target. Yeah, there's no point in background being to like actually applying the propagation to inputs. On inputs. I'm not sure. I mean, people have attempted stuff like that for data generation, right? You backprop into your source data in order to make it more likely.
I forgot the modules for inception. That ones.
Yeah, but that's how we see that same thing in this context. Okay. Any more questions?
Okay, thanks.
Thank you everyone for coming. Thank you everyone for listening. Bye, Tom.